Okay, in this video we're going to be looking at the side-side-side condition. So, again, I'm using Wesley Clark's sketch, and you can see that we see, as always, he starts with a sliders to control lengths. So he has this controlling side 1, the blue side. This controls the length of the red, and this is the green in the Euclidean illustration on the left. And similarly, we have vertical sliders in both cases, mainly because it's much easier to make the sliders and they look better over here in the hyperbolic case if they're vertical, and so it was just as easy to make them vertical as any other direction in the Euclidean. And so we have this. Now, can you mess this up, so to speak? And the answer is yes. You can make it so that the lengths are too small to reach, and in fact we don't get these to add up. And so when does this disappear? Well, it's when these two lengths here together are less than or equal to this length, the other length. So if any two of them add up to less than the other length, there's not going to be enough. Well, it's just not going to work. So that's called the triangle inequality. So if we do have a triangle, it's true that the sum of any two lengths of any two sides must be strictly greater than the length of the third side. And that's also true over here in hyperbolic geometry as well. And so far you notice that hyperbolic geometry, even though it looks a little different, it's behaving really exactly like Euclidean geometry in terms of really every postulate, theorem, and everything that we've done thus far. It's working exactly the same. So neutral geometry, including hyperbolic and Euclidean, basically work the same way. In my trigonometry ultimate sketch, I have basically the same thing here. I used horizontal sliders here instead of vertical ones, but basically the same deal. If we wanted to construct this using those sliders, we would start with the point B, and by adjusting slider A, here we can, point X, we can adjust that slider for the length A, and that goes out here. That's congruent to the blue length. Now we go out from C, we go out whatever length this is, B, and so we know the other vertex. We have two of the vertices. The vertex A has to be on this red circle because it has to be this length away. Similarly, we can go out the green amount on this circle here, controlled by this radius, and of course the point we're looking for is where they cross. Now actually, there are actually two possible places where they cross here actually. So there are two different triangles formed, but if you look at it and you measure their angles, they are actually congruent. So actually we could have chosen either A or A prime to finish up our triangle, and it didn't really matter. Those two triangles were actually congruent. And then of course I investigate that same condition. When is it not going to work? Well, when these two little circles here are not long enough. If they just touch once, okay, then you don't get a triangle. Or if they touch more than once, you do get a triangle. But if they don't touch at all, then no triangle is possible. And that is the triangle inequality again there. And the actual triangle, let's see here. Let's hide the directions. And the triangle congruence theorem, we can think of it in a couple of different ways. If any three positive lengths are chosen, then there will either be 0 triangles possible if the sum of the two shortest sides is less than or equal to the length of the longest side. Okay, so no triangles possible, or one such triangle possible. In other words, all such triangles are congruent, or there's one congruence class of triangles possible if the sum of the shortest two side lengths is greater than the length of the longest side. That's this condition, this shape here. And then the other way to think about it is not if you're given measurements, but if you're just given the two triangles and we have the corresponding parts. For example, these two triangles we know that part corresponds to itself as congruent. If we know these two are congruent, and then these two green ones are congruent, then we know for sure the two triangles are congruent, and of course we get all these angles to match up for free. In my sketch over here, this one is controlled by parameters, and again you just double click on this, change the numbers to whatever you want them to be, like say 2 or whatever. That's too short. 4, and then this one has to be less than 6 then if it's going to work. So there we go, there's a triangle with those sides. And it shows the angle measurements. Of course, this you could do, if you were doing this by hand, you could actually construct this using your compass and straight edge, compass and ruler, and then just measure the angles. But how could you compute those? Well, how would you construct it, first of all? You'd start with your ruler, basically, and measure length A, whatever that is. Then you set your ruler and your compass together to make a radius of whatever B is, 4 in this case. Make a circle centered at C. Then you make a circle centered at the other vertex at B with the other radius, this case 5. And we're looking for, we take one of those two places where they cross and connect it up, and that makes your triangle. And so that's how you would do it by hand. You do the same thing in hyperbolic geometry with hyperbolic geometry tools. But how would we actually compute those measurements? We would use law of sines, law of cosines here. Actually, we use law of cosines to compute the angles here. And then, of course, we could use that formula for the area there as well from trigonometry. And that shows all of the steps of that. Okay, going back to Wesley's sketch, let's look at his next one here. And his also is done by parameter. And again, you can change these numbers here. And the triangles are dynamically adjusted. And then this will also go through the steps. Let's see, hide this. This will go through the steps of, let's see, reset everything. This will go through the steps of constructing, and you'll see the hyperbolic construction over here as well. So start by making your length. Then the next thing you do is you go out a certain distance there that's given to make a circle there, and then finally connect them up. And he also points out there are actually 2 intersection points, 2 different triangles, but all the corresponding parts are congruent. Okay? Now, again, if you've got 2 triangles, this one's back to going by sliders. If the triangles are congruent, do the 2 triangles have to be congruent to each other? If the corresponding sides are congruent, do the triangles have to be congruent? So notice we're thinking about this in 2 slightly different ways. One is we're given some numbers, how many congruence trices of triangles can we make with those specific numbers, and it'll either be 0 or 1 for the side-side-side condition for hyperbolic and Euclidean and spherical as well, by the way. So what we've done so far, the side angle side, the side-side-side, and the angle side angle, the same proofs will work in, side angle side's a postulate, and the other 2 the proofs will work for spherical geometry as well. We'll have to be a little bit careful later on. Now, this is a different perspective. We're not given the measurements. We don't even know what these measurements are necessarily. But if we know the red sides correspond, the green ones correspond, and the blue ones correspond, and corresponding parts are congruent, do you think that they have to be congruent? And the answer, of course, is yes, they do. So let's prove that. So here's a proof written out, and I've got essentially the same proof on the trigonometry sketch, but this proof is nice because it shows the illustrations. Of course, this is done in paragraph form. So we have triangle ABC. Here's a Euclidean on the left, hyperbolic on the right, a triangle down here, and all the corresponding sides are congruent. And so it says corresponding colored sides are congruent. So if they're both blue, they're both congruent to each other, and the 2 reds are congruent, and so forth. On the 2 on the left, on the Euclidean, and then of course the 2 on the right on the hyperbolic. Now, how are we going to prove this? Well, we don't have anything about angles. So if we had some angles, we might be able to do side angle side, or we might be able to do angle side angle. Well, we don't have any. What we're going to do is we're going to make an angle. So we're going to construct a ray AH. Here it is in hyperbolic on the left. Okay. Where's that? Where's the edge? Here's the edge of the half plane. All right. So here it is on hyperbolic on the right, I should say, and on the left, Euclidean. And so how are we going to make it? We're going to make it so that that angle right there, okay, is congruent to this angle down here at D. Can you see it? Do you see the markers that when you press these things? So the marker here shows that that angle and that angle are congruent, in the same way over here in this picture. Okay? And let's do it so that this ray is on the opposite side of line AC from B. Now, how do we know we can do that? That reason wasn't given in the proof, but we can provide it right now. We know we can do that because of the angle, basically the angle measure postulate. The angle measure postulate says given any real number, specifically the measure of angle D down here, there exists exactly one ray on this side, the non-B side of line AC, where that angle is going to go out the same. So maybe many points for H, but only one, that all be on the same ray. So only one ray here, AH, that's going to produce that same size angle as angle D. Now the next thing we're going to do is we're going to go out on this. Once we have the ray, we have a coordinate system for every ray. Okay, and so that's really part of the reasoning here for the proof that he didn't write the details. But the reasoning says we can go out a fixed distance, AB, whether it's over here or over here, hyperbolic distance over here, Euclidean distance over here on the left, and this will make a point K. And so there's a unique point K on this ray AH, so that the distance from A to K is the same as the distance from A to B, which is the same as D to E. So now all the blue distances are the same, AB, AK, and DE, or over here AB, AK, and DE. Same letters on both drawings. Just two different pictures. Now the next thing we're going to do is finish up our triangle here by constructing KC. So construct a line segment here, and of course we know that any 2 points generate exactly one line segment. We have a theorem that says that. And so here we have the same kind of picture here. Alright, so far so good. Now here's what we're going to do. We're going to prove that that we have some congruent triangles. Now what do we know? We know the blue side is congruent to the blue side. We know this angle at A is congruent to this angle at D. Not necessarily the one we started with at A, but this new one for sure. And we know that this red side is congruent to this red one. Well, look at that. We have what? Side angle side for those two triangles. So by the side angle side postulate, let's make sure we get the right order here. KAC is congruent to EDF. Now, corresponding parts of congruent triangles are congruent, so we get a couple other things. For one thing, we get KC is congruent to EF, which is, of course, remember, congruent back to BC. Okay? And we can construct a line segment here from B to K. Now, it's going to cross in the middle there, somewhere at some point. Well, X. It may not be in the middle. X may actually be outside of the triangle. It doesn't have to be on AC. But there are B and K are on opposite sides of the line, so it has to cross the line somewhere. It could be inside the triangle. Could be that A is between X and C. Could be that X is between A and C, or it could mean that C is between A and X. It could be any of those situations, but somewhere in there it crosses. Okay? And this is not going to affect the proof. Now the isosceles triangle theorem, now the proof of the isosceles triangle theorem really is only going to use the side angle side postulate and maybe the angle side angle theorem. It's not going to depend on this theorem, so we can use that. You'll have to prove that. Okay? So I think that's actually probably a homework problem, is to prove that. And what does it tell us? Well, we have an isosceles triangle right here from K, A, B, because these two sides are congruent. And one of the things the isosceles triangle theorem says is that those two angles there are congruent. Now the same picture is going on over here on the right now, so let's don't forget it. Here's the hyperbolic picture for the same thing. And again, we could have between this relationships, K could be in different places, X could be in different places. In fact, I tell you what, we'll put it outside on one, and we'll put it inside the triangle on the other one. Okay? Doesn't matter to the proof. Okay? Now, that's because we had an isosceles triangle. Those two are congruent. Now, similarly, we get these two angles here are congruent. The smaller angle at B. Whether that's inside the triangle or outside the triangle doesn't matter. That angle is congruent because it's a base angle of the isosceles triangle where these two are congruent, and then this is the other side of the triangle. And so we get those are congruent. Well, look at this. Whether you're adding these two congruent angles, these are the same measure as these two, so when you add those, we get a congruent angle at B and at K. The big angle, angle AKC and angle ABC. Or if it's the situation like in this one, where you're having to actually subtract them to get the angle from ABC, it still gives you congruent triangles. Okay, and so now we know that those two triangles are congruent. We may have to look at a couple of cases there to actually write out the rest of the details of the proof. There are a few details left out of this proof. And so what have we established so far? We've established that this is congruent to this one. This one is congruent to that one. That was all given in the hypothesis. But now we know that the big angle up here at B and the big angle at K are congruent. So even if we hide this and we're just looking at this angle up here and this angle here, these two triangles now are congruent by side angle side postulate. Now, congruence of triangles is an equivalence relation. So what have we shown? We've shown that, first we showed that this triangle down here is congruent to the one here. And now we've shown that the one here is congruent to the one up here. So the first and the last one are congruent. And so if you put the corresponding sides together, you get triangle ABC is congruent to triangle DEF. So basically, what did we do? We had a clever little idea. Sometimes the mathematicians might say it's a tricky proof or a trick to the proof. By that, it doesn't mean it's necessarily hard. It just means there's a clever idea that made it work. And the clever idea was we needed to get our hands on some angles because we needed to be able to use the side angle side postulate to prove the side-side-side theorem. And we didn't have any angles that we knew, so we just made one. And of course, why do we know we can do that? Because of things like, essentially it comes from the angle measure postulate and the coordinate system for a line or for a ray, and those two things allowed us to basically be able to set this up to make the construction that we wanted. Then we take this triangle, this new triangle we made, along with the one down here, show they're congruent, and then finally eventually get to the point where that allowed us to get enough pieces to make these two up here congruent. Okay, so that is the proof of the side-side-side. We'll come back next time and start investigating the angle-angle-side situation. And, before I finish off, let me remind you that I think there's nothing wrong with any of these steps in spherical geometry either, for anything that we've done for angle, side angle, or side angle sides of postulate. But I think our proof works just fine for angle side angle and also for side side side. So these two theorems I think will be just fine in spherical geometry as well, and I think the same proof will hold. We may need to be a little careful to be sure, but I think it will hold as well.